Today, our speaker today is Sergey Cherkis, current member, otherwise from the University of Arizona, right? And he will talk about Yang-Mills, Instantons, Quivers, and bows.
Thank you. Thank you for the invitation. So the work I will put today is in this two texts, one in general differential geometry and the other one submitted last week. And this being analysis seminar, I decided to focus on the analytic side of the issue, while the subject directly relates to quantum field theories, representation theory. So many of the subjects that I'll touch, but only lightly. So in order for me to get the formulation of the problem, let me start with an action sequence, which introduces the main actors in this play. So as a warm-up, let us consider Euclidean R2. And I want to think of this R2 as complex plane. It has complex structure, and it has Euclidean metric. Once you have complex structure and Euclidean metric, you can introduce symplectic structure. You immediately have symplectic structure. Metric, you should have complex structure in one of the entries.
What is that complex structure?
Just multiplication by I, okay, or minus I, it's up to you. Then complex plane has a symmetry, and we can rotate it. And that symmetry, of course, respects complex structure and the metric, and as a result, is a symplectomorphism. So the symmetry generates the rotational vector field, and if we feed this vector field into symplectic form, then it's differential of some function, and that function is the moment map. So in this case, long story short, this moment map is 1/2 this product. So what we have now is we have, if you wish, another coordinate on the complex plane. So one coordinate is the moment map, and the other is the angle. Right? This is a projection of the complex plane onto the array of positive numbers, and for every positive number, the orbit is a circle. The circle of given variables. When you approach the origin, the circle shrinks to 0 size. So that's the view of the complex plane projected under the moment map onto our non-negative. So in particular, we can rewrite the usual Euclidean metric in these new coordinates. And it has this form which might look singular, but of course it's just coordinate singularity, it's a parent singularity. So now that we described the plane in this radial coordinates, let me introduce radial coordinates on the 4 dimensions. So when you think of R4, you can think of it as a quaternionic line. And now you have 3 complex structures to play with, I, J, and K. So these are quaternionic units. If we multiply M, J, we get K, and square of each of them is -1. And there is usual Euclidean metric. And now we can play this game, but 3 times, having 3 times more fun. We can introduce a form for each of the complex structures. So there will be 3 symplectic forms. If we understand the I, J, and K as acting by multiplication on the left, then we have 3 multiplied by any quaternion we wish on the right, and this will be symmetry. And if it is known 1, then it will be symmetry of the metric. So there is also symmetry here, and I'll just pick Z to the I, let's say K prime. So the symmetry respects all three of these symplectic forms. And by complete analogy, we will get three moment maps, Ui, Uj, and Uk. And it's convenient to package them into an imaginary, few imaginary quaternion. Let me call this T. So now my radial coordinates. Before we took a plane and mapped it into an array. And now we have R4 mapped to R3, imaginary quaternions. So if you wish, now we have three radial coordinates, values of the three moment maps. And if you have a generic point here, the orbit of that symmetry gives you a circle. So for example, if you are to choose a ray here, then over that ray, you will have a complex plane within the quaternion class, just the way you had before.
Is it clear, except for dimensions, why you get a circle and not something more complicated just above it? Because you can have more than one gauge symmetry.
Of course. So we committed to one gauge symmetry, and that produced.
Oh, okay.
So
It's just for that specific.
You can choose another one, and you have a different way of covering your toolspace.
And why do you write it with the tensor, the UI tensor I? Is it?
Well, just to keep track where things take values. So that's. I want to assemble it with quaternions. So quaternions act on some space. Don't like you can erase the tensor. This is
No,
in this case.
Just I'm trying to understand what's.
Well, in what's coming, there will be some larger space we can act on, and the story generalizes. What I described here is a general generalization of symplectic reduction to hyperkähler reduction.
So the new I, new J, new K are what object?
Are the moment maps.
No, but what is it? Previously it was a scalar map. So now it was a scalar map from C to
Exactly. So
from C to R plus.
the moment map just as here, the moment map takes values in the dual of the Lie algebra of your symmetry group.
Of the symmetry group.
Yes.
So they get values in Z in this case, or R?
No. Yeah, in R.
In R?
Just R.
They get values. Okay.
Strictly speaking, IR and it's getting more.
Yeah.
Well, if you choose a slightly different way, then you will get well, similar homotopic cigar shape. In particular, if you rotate it all the way, if you look at this ray, you'll get a similar cigar. In particular, if you think of your quaternions as a pair of complex numbers, so if you write the quaternion, I call it C, as U plus J B bar, for example, then these will be simply two complex planes in terms of these coordinates. This will be D equal to 0, and that will be U equal to 0. So in particular, from this, it's very easy to see what the intersection number between them is. Well, the intersection is 1, you just have to decide on the sign. And our symmetry group rotates both of them in the same direction. But our complex structure acts on them in the opposite way. So the intersection number is -1 in this case. That's pretty much all I wanted from this picture, all the topology I want to from this picture. But what is important is that we essentially took R4, we view it as two complex planes. We can rotate both complex planes in opposite directions. And that fibers all of R4 bicircles. And the circle vibration is essentially Hopf vibration. If you restrict to a specific sphere, it's a Hopf vibration, the Hopf number 1. Well, of course, just as earlier, we can take Euclidean metric on R4 and write it in these nice coordinates. So in these coordinates, it's like dt squared over t, which is just distance to origin, and almost t plus keep it. That's on one form, which is one form along the fiber. So if you like locally, you can write this form as d phi plus some local one form where you can think of it as a connection on this Hopf vibration. And as usual, there's sort of apparent singularity, but we know that this is just flat metric, so we can get rid of it by changing the coordinates.
This is the R2 case, or is this the R4?
This is R4.
This is the R4.
Yep.
Where did the new connection? Like, why didn't you have the connection in the R2 case?
Well, because if you fiber a circle over an interval, any such vibration is trivial.
Okay.
But if you fiber a circle over a two-sphere, then this is exactly the Hopf vibration. The classic example of this non-trivial vibration, and it's hard to avoid in this case. And in a sense, much of this analytic story will be entangled with topology appearing from this vibration. It's different forms.
So the connections that you get are up to some homology class?
Well, in this case, there's concrete projection. There is a metric. So a metric induces Ehresmann form on that, and that is fixed. But if you try to change your coordinates locally, then it will get fixed, of course. Right, so now, what did we do? We simply wrote a metric on R4. And now, given some talking, discovered that you can deform it and still keep the space hyperkähler. That is, locally, you still have I, j, and k, and moreover, they are integrable complex structures. So for our purposes, we can simply just write the metric. The metric is called our metric. This metric on R4. It has very similar form. Some b. Exactly the same one. So before R4, this was 1 over t. So as a result, for example, if you look at the size of the circle of Hopf fiber, as we go to infinity, it grows. It's unbounded. It grows together with the base. And in this case, we simply add a constant to this. So this is Taubnat metric in Gibbons and Hawking form.
So this is a deformation which preserves the hyperkähler structure.
Exactly. So this is still hyperkähler space, but before we had a three-dimensional sphere, which as we increased the radius was growing. All of it was
Sorry,
growing.
there's a dt there. So why shouldn't there be quadratic in t?
Thank you. Yes. So what happens now is as we increase the two sphere of the base, the fiber as t tends to infinity, the fiber gets to some finite size. So with infinity, we get a squashed sphere. The base out of 3 is growing, but the fiber stabilizes to given size. And moreover,
Can you, is there an intrinsic definition of this metric in terms of symmetries? I mean, you wrote down an example as deformation. You're calling it hypercalars at the so is this the only one on R4?
well, this is a subtle question depending on what we demand from infinity. Until we specify
okay.
infinity, there's no. So let me return this to this question right after I give the next generalization.
Okay, thanks.
Yes, so Gibbons and Hawking were looking for all such hyperkähler metrics, and they started exactly with this. They started with the non-Zatz, which has one symmetry. Look at the moment map, and you write the hyperkähler metric on that. And if you follow this path, then the next step is multi-Taub-Nut. Taub-Nut sub K or K-centered Taub-Nut. It is given by exactly the same expression. Except now, instead of something interesting happening at the origin, you pick K points. Let's call them U1, U2, U3. In R3. And you write your V to be a constant, then plus 1 over 2 distance from T to U1. So as Gibbons and Hawking concluded that this is again a hyperkähler metric. When you approach any of these points, any of these nuts, then you see that in the leading order, you recover this metric on R4. So all the singularities are apparent. And this is a smooth manifold, so long as all the nuts are distinct. Next, if you look at a sphere surrounding only one of them, the preimage of that sphere in this Taub-Nut space is Hopf fiber, just the way we had it before. So there's Hopf fibration of Hopf number 1. But if you look at infinity, if you look at very large,
My hearing is not so good. Are the news called nuts?
yeah, usually people refer to this.
Okay, so Taub-Nut is not a name. It's Taub is the name, and Nut is these news.
Well, it stands for Newman, Unti, and Tamburina. But when people studied this space, they discovered that there are 2 types of singularities that can develop, apparent singularities. One of them are called nuts, the other are called bolts.
Okay. All right.
Right. So if you look at a very large sphere, then over a large sphere at infinity, you have Hopf fibration of Hopf number K. You also have similar story to what we had before. If you look at a ray originating from any of these nuts and going in generic direction, so it misses all the other nuts, then over that, there is the cigar shape, just as we described before. So for each nut, there is its own cigar. That again will play a role in a second.
So you probably explained, so this is going to be a singular metric or not?
This metric has apparent singularities near the nuts.
Yes.
But if you look at what it looks like near the nut, then it has this form. Right? If T is very close to, let's say, U1, then only this term matters. So
is it, and you explained, is it obvious why this still has the hyperkähler structure?
It's not. The way you described it's not.
Okay.
Yes. It's, if you think of it as sort of resulting from some moment map, then it's kind of one step. Right, so this is the prototypical example of asymptotically locally flat hyperkähler manifolds. And there is a theorem of Minerve showing that these are the only ones. So this is the only hyperkähler metric with this specified asymptotic. So once
So how did Hawking get in? I mean, this is related to general relativity, or?
Hawking was interested in formulating Euclidean quantum gravity. And he had this idea that if you look at the universe, as you approach to the early universe, in order to describe the wave function of the early universe, you should simply cut it off, look at this Euclidean slice, and then extend it into Euclidean solution of Einstein equations, which is smooth. And then you should sum over all possible such extensions. And as a result, you get the wave function for early universe and then propagate it further on. So this is sort of his path integral formulation of this. And this, in a sense, gives the origin for one related activity, this finding all hyperkähler spaces. In a sense, for quaternionic geometry, these gravitational instantons or hyperkähler manifolds like this, which are smooth, they play the role.
I didn't understand the behavior at infinity of these tau nut K. At infinity, not at the nuts.
That's right. So at infinity, they all look like Hopf vibration with finite size fiber.
So when you parameterize these, the number K will emerge out of your looking at infinity. You'll see how many nuts there are.
Exactly, exactly. And I'm about to describe how they appear at infinity. Yes. Yeah, so there's a whole slew of such spaces, and they have very peculiar relations to various other fields. But for today, I'll focus on the tau nut. So let me address this question of infinity and the topology of the space, so we can visualize it easier. There is Hausel, Hunziker, and Mazeo compactification of the space. Which makes some parts of analysis a little easier, and also gives a nice way of visualizing its topology. So if we call that space M, compactify the space and obtain a smooth manifold effect. You can think of it as M union with a two-sphere, where for each direction in R3 toward infinity, we introduce 1 point. So remember, if I have some direction, then I have kind of a cigar shape in that direction, after speaking. And all I do is I add 1 point in that direction, and I close this cigar to a sphere. So to remember that this is infinity, I'll call this C infinity bar. And in particular, every cigar in M, every C sigma, now compactifies sigma bar, which is a two-sphere.
What happens if you collide?
Sorry?
What happens if you take a direction where you collide another nut?
Exactly. So if you take two nuts and connect them by an interval, of a generic point of the interval, you have a circle fiber. As you approach one, fiber shrinks. As you approach another, fiber shrinks. So there is a homology cycle there. So let's say this is sigma plus 1. Then I have homology cycle called delta sigma. And you can see that it's homologous to what? To C sigma plus 1 times C sigma. So for example, the second homology of tau nut is zk minus 1. Its basis is given by these consecutive sigmas. While the homology of m bar will be zk, and that will be given by sigma bars. The relation between the two is dictated by infinity, which is exactly was Peter's question. So let's look at m, and let us cut out. Right before, so that there was a projection of this to R3. Let me give it the name 5. So I'll take some ball of radius, or large radius R in R3. I can pull it back, look at its image. So if you throw away a very large ball which contains all nuts, then this is homotopy to R cross length space. And in a sense, that's our infinity. So that is what, another manifestation of what was mentioned before, that our infinity looks like Hopf vibration of Hopf number k. This file. So in some sense, the spaces M bar and M, to me, reincarnations, like avatars of UK and SUK. And this infinity plays the role of the center of this UK. In fact, if you look at
Why does this look like UK?
well,
Are you referring to unitary group? What's
yes,
okay.
exactly. Yes.
Okay.
So there are a few connections here, and if I try to avoid physics,
Well, maybe if that's taking you too far afield, maybe.
well, there is one
talk about
good way
that.
of getting there. You can try to compute homology of this space of n bar, for example.
Yeah.
And that is usual Meyer-Vittorius. Meyer-Vittorius involving M and neighborhood of infinity.
Yeah.
And when you simply look at that Meyer-Vittorius, so what do you get? You get some H2 of the intersection. You'll get H2. H2 of the neighborhood of infinity. And H1 of the intersection of M and the neighborhood of infinity. So this will be spanned by sigma bars. So this is simply Z, like this is the sum. That will be K, and this spanned by the basis is sigma bars. It's the usual lattice, and it's exactly that character lattice of UK. While here, Z K minus 1, and that is spanned by delta sigmas, which are the differences of sigmas. And n infinity shrinks to this sphere that weighted at infinity, which is simply the sum of that is a sum of all these sigmas. So it's the diagonal in that, and that, if you like, that corresponds to U1 sitting inside of UK. And that is spanned by sum. Well, here, this intersection is, well, a deformation retracts to space. So here we get ZK, which is the sum. There's more direct connection of this with UK, but well, the best I know was string theoretic interpretation of this space. But so far, it just appears on the level of all right, so this was sort of a long action sequence to introduce main character, which unfortunately I have to go through to simply describe what the space is that we studied. And this is not the most general space. There are other ALF spaces. There are D and A type, but this is the simplest to write.
There are other what spaces?
Asymptotically locally flat.
So there are other compactifications, or?
Well, the compactification depends on what property of the space you would like to use. So for analysis, we use this compactification. And when we try to give algebra geometric description of the space, then we use entirely different compactification of the space, which are called to these. You can think of it as a blow of P1 cross P1 at key points. Right, so now that I have the main character, let's describe some of the motivation. The motivation is threefold. One is that these spaces, and what I'm about to describe, instantons on these spaces, have direct relation to quantum field theory in their various spaces of vector. But geometric motivation is from studying hyperkähler manifolds. And we insist that hyperkähler manifolds that we study have if you look at Riemann tensor, then its L2 norm is finite. So such spaces fall in different categories depending on how they behave at infinity and on complex. And the first one is ALE. Second class is ALF, ALG, and H. And what distinguishes them is how fast a ball of large radius r grows with I. So if it grows maximally, in the volume, if it grows maximally as r to the fourth, then the space is called ALE. And all such spaces were classified by Kronheimer, and they come in A, D, and E type. If it grows as R cubed,
So okay, yeah. So Kronheimer classified all such spaces.
yes. If it grows as R cubed, then they come in two series. There's A type and D type. A type I just described in detail. This is multi-tailed knot. In D type, the first example of D type was discovered by IT and Hitchin, some modular spaces of monopoles. And all the other D-type metrics we wrote with Hitchin, and we found their realization with unlock acoustic. Next, we know that there is nothing in between. There is no volume growth in between. So next, for AL G spaces, we can have some volume growth between, well, less than 3 and greater equal to 2. The LH spaces, anything with volume growth less than 2. So all these spaces relate to quantum field theories. The spaces of vacuum, Coulomb branches, Higgs branches, there are many different realizations. Just to give some association, ALF spaces relate to three-dimensional symmetries, ALG, four-dimensional spaces. One, and I can tell much more about all of them, but I just mentioned this connection here. I want to focus on the next column. What kind of combinatorial objects appear in description of this? ALE spaces, in fact, this is Kronheimer's construction. They all described in terms of quivers. And quivers are essentially points and arrows connecting. ALF spaces are related to bows. That's what the story will be about today. ALG spaces relate to slings. And the LH spaces relate to monomoles. The only reason I mention this is that all of these are steps in generalizing the notion of a quiver. So these, for example, quivers involve some algebraic equations. Bows involve some ODEs. Slings involve some PDEs, like Hitchin systems. And monomoles involve PDEs. Well, these are in 2 dimensions, this is in 3 dimensions.
So these are equivalent versions of these manifolds. I mean, this is an equivalent way of.
So these modular spaces appear.
Yeah.
These spaces appear as modular spaces called these objects.
Okay.
But what I want to emphasize today is that these objects catch much more than just a space. They also give you a construction of all Yang-Mills instantons on that space.
So there's more information.
That's right. So let me just define quickly what Yang-Mills instanton is. So Yang-Mills instanton on manifold M is there, a bundle on M, permission bundle on M, and a connection, such that two things happen. The connection has a curvature, A. This is a 4 manifold. And you can think of this curvatures as a 2 form valued in the algebra. So if you apply Hodge star operation to it, you'll get dual form. So the first requirement is that this 2 form is undercell-dual. And second requirement is that it is L2. In other words, the integral of f squared, trace of squared, over m is fine. So if you like, the task is, well, there are 2 stories, one classifying such manifolds, and then constructing various instantons, Yang-Mills instantons on them. If these manifolds appear in kind of Euclidean description of quantum gravity, in Hawking's description, if you have gravity which also involves some gauge fields, then you have to understand both the space and these. So next, let me try to sketch what we know about instantons. So we'll focus just on these. Moreover, for concreteness, we'll specify it to tau naught. Sorry, I'm going to generalize any L space. And describe what is instantons, what we know about it. So first,
In your classification on the board top left, when alpha is say between 2 and 3 or between 0 and 2, is it any number or is it some specific numbers that come up?
yes, so our current state of knowledge is that we know examples of these spaces. And some people conjecture that these are all, but there are no theorems about what the spectrum of these alphas
I see.
Actually is. So there are some theories about the gaps
Mhm.
that I indicated, but nothing below.
Thanks.
Right, so let's start with what we know about the Elise. So there's this core theorem of Uhlenbeck. It states that for any instanton on R4, there is a bound on the pointwise norm. R4, and in fact for any the pointwise norm of the curvature decays vertically. So before we approach the story with instantons on the LF space, we have to generalize this theorem to that setup. So in this case, the volume grew maximally R to the 4th. In ALF space, so in multi-tau knot, we have R3, and it's asymptotically divided by a circle of finite size. So now, these the theorems. And all these theorems are proved with Andres, Lorraine, Kubash, and Mark Stern. So for instantons on any ALF space, there is one technical assumption, which I'll explain in a second, with generic asymptotic holonomy. Curvature is quadratic. Let me explain what generic asymptotic holonomy is. When you move very far in the base R3, there is a circle over that point. And in particular, you can look at holonomy of the connection around that circle, around the phi. What we presume is that that holonomy, or the conjugacy class of that holonomy, has a limit if we move in at least one direction in R3. As we carry it to infinity, it kind of stabilizes to something. And then it is, well, that's where its genericity is, that it's a regular orbit. So along some direction in R3, we get a regular holonomy.
What do you mean by regular holonomy?
It means, well, if you think of it as an element of UN, then all of its eigenvalues are distinct. So we impose it for simplicity, but the whole construction, I believe, generalizes to degenerates. So in particular, another result we proved is that if there is such a direction, then in fact, this conjugacy class is the same in any other direction. This limit exists in any other direction, it's the same conjugacy class. So in particular, if you have any instanton connection, then there exists a local plane. Now instanton bundles. Such that we can write fairly explicit form, asymptotic form of this connection, such that instanton connection. There are some of the billion ones. So each of them. So at infinity, as I said, the holonomy of E around the circle has distinct eigenvalues. As a result, we can take this E and split it into eigenbundles of holonomy.
So your analysis starts out by assuming just that the curvature is finite, and from that condition, there will be some finite K for which this is true. Right? When we start out, there's no K.
Well, we start out on some space.
Yeah, we started, I mean, you're classifying ALFs with curvature finite.
You fix some ALF, and then you look at some bundle and some connection on it, such that the connection is under self-loop.
Yes.
So
what I'm trying to, before you had, this is all new to me. So you had these topological spaces, which were these hyperkähler metrics topologically, which were these Taub nut K.
Yes.
There was a parameter K, which is not specified when you start out.
Well, once I get to Yang-Mills instantons, I choose a specific space, ALF. And now on that space, I look at bundles and connections.
Oh, that's where you give yourself a K. Okay.
And my only requirement is that that connection has finite into curvature and it's under self-loop.
Okay, but you're giving yourself the K then. Okay.
That's right. Then first,
Well, you'll describe them later. Are these bows going to describe these spaces of the ALS later?
So bows will describe both the space and the full instantons on it.
Yeah, so the fact that the growth is not is 1 over R2 instead of 1, I mean, is weaker is because the space is actually smaller at infinity, right?
Exactly.
Okay. Yeah.
Yes.
Okay, thank you.
And this bound is very sensitive as you go through this list. It's very, very sensitive to behavior.
I see. Yeah.
Yes.
Right. Are you going to tell us how it's done?
I can. Yes. I love this story, but well, today I plan to focus on the bows, but yeah, I'll be happy to go through this proof as well. In fact, even before proving this, we have to prove that norm of F decays at infinity. Even that part was not trivial.
That's right. That's right. No, it's not clear. All you have is an L2 bound.
Yeah. So we started from L2,
right.
Then from L2 we proved L4. That is immediate from Sobolev inequalities.
Right.
And then we had to do some Moser iteration to get from L4 to LP and then to L infinity.
Right.
So that was quite subtle. It took us a while.
Oh, sure, sure. I see, but you did the Moser iteration infinity. Okay, that's interesting.
That's right. And then this is the first paper that I listed today. So we look at this bundle, and we look at this bundle again outside of some black hole. And because holonomy is has distinct eigenvalues, we can look at eigenlines of that. And as a result, bundle splits into line bundles at infinity. And the connection, so each of these line bundles, each of EI, now be thought of as a pullback, of some power of a Hopf bundle over the base S3. And once we've presented it this way, then it will be connection, pullback of connection on that Hopf bundle, minus I lambda I, which is logarithm of the holonomy, plus some integer I over 2t. The bound here again, the corrections are all for the 1 over R squared. Now, what is interesting here is that the way you write this, of course, depends on what sort of frame you picked. In other words, this bundle, this line bundle that I described, is a bundle over essentially the length space at infinity. Let's think of it as, let's cover, let's say bundle over S3. If you have some bundle over S2, the base of the Hopf vibration, you can pull it back to S3. You'll get line bundle on S3, but any line bundle on S3 is trivial. So these numbers, for example, will depend on your pullback or your trivialization. And over length space, these numbers, lambs, will be really defined mod k. There is k distinct bundles over the length space. That's right. So I'll mention, in particular, if you look at these combinations, lambda J and J, and each of these combinations is really defined up to a change of frame. And the J is shifted by L and MJ. So really the invariant object there about this bundle is MJ mod A. So if we are studying, just to remind you, we are studying UN instantons. 1000K. And by looking at infinity, what did we get? We obtained n different numbers for each eigenvalue of UN. We get n different numbers, which is really well defined mod k. We have some MJ hat. So each MJ hat is between 0 and k minus 1. So out of these numbers, we can construct a Young diagram, which is k equal 4 and n equal 5. Say 5, 3, 1, 1. So this will be Young diagram, which I'll call Y co-balanced. And this keeps track of infinity. We also have interior. What keeps track of interior? Well, there are analogs of classes, except You can take trace F and integrate it over each cigar. Except now our manifold is non-compact. This doesn't have to be an integer. This will be equal to sum of lambda j's over L plus some integer. Call this C Gothic C sigma. So these C sigmas associated again, each of them is associated with some nut. So let's order them. So the sigmas are, if you look at them, mod n, then they will give us k numbers, each of them between 0 and n. So now we have Young diagram in n by k. It's 3. 4, 3, 1, 1. This is what I'll call Y balanced. And in whatever you test, the relation between the two will be that one is greater than the other transpose. And all of them will relate to the bow in a second. But so far, I'm just specifying what should you fix in this problem. What is the topology that you fix before you start doing analysis? Okay. So you specify these numbers n, which I call monopole charges. You specify lambdas, which are asymptotics of the holonym, and you specify first Chern numbers. And there's one more number that you have to specify before topological part is fixed, and that's the instanton number. What is the instanton number in this case? At infinity, we got a flag consisting of these line bundles. It's a flag because we can order our lambdas, for example, 0 and 1. That's an order that gives us a flag. So the instanton number get out of it is an element of 5, 3 of this. So now I can finally formulate the problem, and that is finding all anti-cell dual connections with these numbers. And out of time, I'll simply sketch it now. That so the detailed relation is some nonlinear version of Fourier transform, which generalizes Atier, Kitchen, and Manin, and now all sort of in one package. And what you should do is you first find purely abelian instantons on tau nut. I call them kind of tautological bundles associated with them, which have purely abelian solutions. In a sense, each nut has one Poincaré dual 2 form, and that Poincaré dual 2 form is a curvature of some line bundle. And then, if somebody gives you an instanton, out of that you can construct a Dirac operator. Checks the 2 sections of E tens of S. And what you do is twist that with your family of abelian instantons. You just take line bundles, the topological line bundles, and tensor it with E. This gives us a family of line bundles over a circle parameterized by S. One of our theorems is the index of this family. Now this index depends on S, and it can change either at points where we are forced to tensor various bundles corresponding to each of these cigars, or it can change at points where holonomy, this now shifted holonomy, is trivial at infinity or has eigenspace. So as a result, what we get a circle like this, such that there is a bundle over each subinterval over that. So if you take this circle and cut it into pieces, with maps in the ends, then each of these has some lambda points dictated by asymptotic polynomial. Then from this index bundle, you'll recover the actual bundle over each of these subintervals with various matching conditions. And moreover, this bundle is bundle of L2 sections on the tau map. So as a result, if you have some section, say psi I, L2 sections, and another section psi j, you can multiply it by one of the coordinates on your R3, let's say T1, and project it back on the kernel. So that gives you an endomorphism, which depends on S, of this bundle. We'll get 3 endomorphisms, and we'll also get a connection, which is induced by simply DDS. As well as various gadgets associated to each lambda and the maps between them. And the result is that they satisfy various equations. These, for example, T's will satisfy the Naum equation on each subinterval. And that is the first example, basic example of a bow. So a bow consists of these oriented intervals connected by arrows. The representation of a bow consists of choice of lambda points and bundles over subintervals. And then if you look at endomorphisms of triplets of endomorphisms of this bundle, T's, and perform hyperkähler reduction under the action of the gauge group, then you will get what I call a bow solution. Space of bow solutions is moduli space. And what we prove is that this moduli space is isometric, the moduli space of instantons. And moreover, given this bow data, one can construct instantons explicitly. And moreover, there is inverse of this transform. And the last paper is exactly about this. Given bow solution, you can actually go back and reconstruct the instantons. So I think I managed to say about a quarter of what I have, but I'll stop here.
Questions?
So ADHM, one can think of them of that as a linear algebra data description of an instanton, or you can also phrase it in terms of vector bundles on P2 as some additional data. Is there a similar algebra geometric reformulation of what the things are?
Exactly. So we have a sequence of papers with Jacques Coutebis, which instead of this analytic approach takes algebra geometric approach. And that relates to Peter's question, is that this compactification that we picked here, even though in Tau-NAP we have we had a whole sphere of complex structures, this compactification is not compatible with any one of them. So this M bar is not a complex manifold in any of those. So that's not amenable to algebra geometric approach. Instead, you should think of it as starting with, let's say, R3 process 1. You can think of R3 process 1 as C plus C star sitting inside of P1 plus P1. And if you want to get the multi-tau nuts out of this, you pick one of the P1s representing infinity and start blowing it up. If you blow it up at k points, that would be the good compactification in which you can do algebraic geometry. And in other words, instanton on this space gives you a holomorphic bundle on that space, on blowups, with particular flag fixed at infinity. And out of that, we extract the monad description of these instantons. Of course, it knows almost the same information except for analytic estimates and all that, but it probably has some other reincarnation.
Can I ask about this decay estimate for the curvature? Is there a guess, or I mean, can one guess naturally what the power should be from the volume growth? Or
well, that's sort of the problem, that if you know that it decays as a power, then yes, the conservative guess is saying that it is dictated by harmonic function on your space. And then it's gradient of that harmonic function. Right? And then for that, so for your space multi-tau knot, so this is essentially R3 as far as harmonic function is concerned. It's allowed exponential growth. And then you take R3, takes its gradient, and that is good guess for the metric. But then, as it turns out, just proving that it is not just polynomial, proving that it's decaying at infinity is quite a bit of work. And then proving that it's polynomial is additional.
So you mentioned some iteration scheme. Is this like a natural iteration, or is it one of the Moser type iterations?
It's Moser iteration.
Moser iteration.
Yes.
Can you return to what those alphas were? I'm kind of curious. In that's the possible growth rates were.
Oh, yes.
Maybe it's not there anymore, but you have examples. I mean, are there countably many examples? Are they algebraic?
Yes. So these spaces are all hypercadal, of course. So in particular, so the spaces we spoke about today, they're essentially defined by a circle. We only want something. ALG spaces and ALH spaces are divided by a torus, which in a very special complex structure it's an elliptic curve. The only distinction between them is the deficit angle on the base.
Mm-hmm.
So for these spaces, the deficit angle is less than 2 pi, and here the deficit angle is 2 pi.
And the angle could be any real number then.
Well, for the examples we know, it's not. And in fact, so for example, all of these spaces fit neatly into just Del Pezzo surfaces. Or if you like, they're all the examples we know. They're all complements of some fiber in a pencil of cubics in P2. So each of them relates to some. Well, there are many interpretations of this. For example, each of them relates to some Pendelet equation.
Mm-hmm.
But what I described now relies on one particular complex structure.
You say Pain-Lavey, is that what you said?
Yes.
Which Pain-Lavey?
All Pain-Lavey is here.
All of them come up. Mm-hmm.
Yes, and moreover, 3 of these spaces appear as discrete. So
mm-hmm.
it's
okay. Mm-hmm. Interesting. Mm-hmm.
And for example, these tricks that I described, this generalization of ADHM transform, kind of Fourier transform, for all other spaces, they kind of take you to some simpler object. You go from self-duality equation in 4 dimensions to, in case of ADHM, to algebraic equation, in case of a boat, to NAV equation, or Hitchin equation. But at some point, you get to objects which are actually kind of self-dual. And here, you can no longer use, once you perform transform, the result is not an object which is simpler. So in this case, you have to study something which has extra SL2Z action, which acts on isometry on various modular spaces. That's this monowall objects they described. That's actually
everything in the end is number theory. We know that. I think you said SL2Z, right?
Yes, but this is SL2Z, not related to this SL2Z. This is another SL2Z in the story.
What happens in the case when the holonomy doesn't split into discrete into eigenspaces? I mean,
Yes, so.
So
I
that
believe
must be in the compactification somehow.
That's right. I believe that the curvature decay is still the same. It just requires some more work that we plan to be doing. But in terms of the bow, it turns out to be a fairly simple generalization. So for a bow, I was describing that these are intervals, and essentially each interval corresponds to a line to a bundle over the length space of infinity. So in our case, we have S3 not ZK. So each of these intervals symbolizes a particular line bundle of that space. And there are maps between them. And in our case, we're also picking lambda points, which are distinct. We will also recover an index bundle over this. That means that we need to give a function which is integer value function, locally constant, and can change across the points. So non-negative integer value function. So essentially, we give some bundle over these spaces. And if there is a lambda point where the bundle does not change rank, then in addition, we have to assign some auxiliary space, W lambda. And essentially, this is the kernel, bounded kernel of the Laplacian over the space. So what happens if there is some degeneration of lambdas is that if lambda has, is non-degenerate, then this will be one-dimensional space. And if it has high degeneration, this is a larger dimensional space that we have to assign here. And if you have some rank change, then you'll have to assign some sort of Young diagram to this, which tells you how ranks kind of infinitesimally descends here. So if this point has multiplicity, if it has multiplicity 2, for example, then you have to describe exactly how infinitesimally this rank decays. So there's some flag sitting at this point.
I see.
And what I enjoy here most is that both takes this information, which in a quiver is bunched up at one vertex, and spreads it out, and you can see how index bundle behaves.
Thank you.
Good. There are no more questions, and thank you again.